All right, so this video we're going to talk about, well, just kind of introduce the normal distribution, and we'll be talking a lot about the empirical rule, the 68, 95, 99.7 triangle. We'll talk about percentiles, not a lot of detail, but just kind of mention it. And we will look at quartiles. We'll mention quartiles and margin of error. All right, so first let's go ahead and get started. So the 68, 95, 99.7 rule for the normal distribution, which is the empirical rule. So what it's saying is if we have a normal distribution, now when I say a normal distribution, that means if you had data and you plotted it, it would be mound shaped like this. Okay, it would make a bell-shaped curve. So what it says is approximately 68% of the data items fall within one standard deviation of the mean, 95% within two standard deviations of the mean, and 99.7% fall within three standard deviations of the mean. Now, don't worry if that didn't make sense to you. I'm gonna go over it and explain it, and we'll explain it through examples and stuff like that, and it'll clear up. So first, before we get into some examples, let's just look at what we mean by that. So here's a normal distribution, okay, and then you can see here this is our mean, okay, that's the mean, and then this is one standard deviation about the mean. See this is one standard deviation, and this is what we would consider two standard deviations about the mean. So what they're saying is if you look at one standard deviation about the mean, that would be 68% of the data. And what this is, that is just the area under this curve here from -1 here to this 1 here. Okay, so like if you looked at just this area right here, okay, if you were looking at that area, that's what it would be, 0.68 or 68%. See, the area under the entire curve is 1. Okay. All right. And then if we go on out to two standard deviations, that would be 95% of the data items are within two standard deviations. And then within three standard deviations, it's 99.7% of the data. And all it is really is it's area. And in this section we will learn how to get to z-scores and stuff like that and all that. And the lecture after this one is where we get into the problems and converting to z-scores and going to the z-table and looking at all that stuff up. But right now it's just introducing it to you. Okay. All right, so let's look at this. It says male adult heights in North America are approximately normally distributed with a mean of 70 inches and a standard deviation of 4 inches. Find the height that is two standard deviations above the mean, and then find the height that is three standard deviations below the mean. Okay, so one thing I'll say about problems like this is the first thing I would do is I would draw it out. Okay, so let's draw this. So here's our normal distribution because it tells us it's are approximately normally distributed. Okay, see if I can't draw that maybe a little better. Okay, so something like that. And we have a mean of 70. So this is 70. So I think this will kind of help you understand some things. So we want to find the height that is 2 standard deviations above the mean. So that means this way. All right, so let's do this. Let's go 1 standard deviation above the mean. So if I go 1 standard deviation above the mean, that would be 74. And if I go 2 standard deviations above the mean, that would be 78. All right. Now, how do I get that? Well, remember, this is the mean, and here is your standard deviation is 4. So 1 standard deviation would be 4 units, and then I go another standard deviation, so I go another 4 units. See that? Okay. So for part A, that would be the height would equal, well, we can see it's 78, but let's write it out. What did we do? That's going to be 70 plus. Now, what am I doing? I'm going, how many standard deviations? 2, right? 2 standard deviations times the standard deviation. So it's the standard deviation times how many standard deviations I'm going above the mean. And so that would give me 78. See, 4 and 4. Or I've got 2 4s, so 2 times 4. All right. Well, what about this? 3 standard deviations below the mean. Well, look, you can draw it out. Let's do it. Let's do it in red. So if I go below the mean, 4, that would be what? 66. And then if I go another 4, that would be what? 62. And then if I go another 4, that would be what? 58. See, this right here is 1 standard deviation, 2 standard deviations, 3 standard deviations. All right. So for part B, the height would equal 70. Now I'm going below the mean, right? So that's going to be minus, and the standard deviation is 4. And how many standard deviations am I going below the mean? That's 3. And so 70 minus 12, that gives us the 58. All right. See, this really isn't that bad. If you will just draw it out like this, okay, it makes it so much easier to work instead of just trying to go straight to this. Draw it out and see what you have. It makes it easier. All right, so let's see. What about this? It says male adult heights in North America are approximately normally distributed with a mean of 70 inches and a standard deviation of 4 inches. Find the percentage of men in North America with heights. Okay, so between 66 and 74, between 70 and 74, and above 78 inches. All right. Now, I told you, to draw these out because it'll help you. Now, to me, this is really important to draw this out on problems like this. So let's draw this out. All right, so there's the mean. All right, and we want to know between 66 and 74. So what we're looking for is that area right there. That's what we want to know. Okay, see, because that's what they asked for. Find the percentage of men in North America with heights between these two. And it's this percentage right here. All right. Now, how do we know what that is? Well, we know the mean is 70, and I have that. I'll tell you what, I'm going to write this. I'm going to write this in a different color. So we can just distinguish the 70 from the other numbers. Okay. Now we know the standard deviation is equal to 4, right? That's our standard deviation. Now in this problem, if you notice, I need from 66 to 74. Well, do you see how this is 4 units and this is 4 units? Okay, so this is one standard deviation and this is one standard deviation, right? So you can see that 66 and 74 is one standard deviation about the mean. Okay, one standard deviation about the mean. So if you come back up here, remember, one standard deviation about the mean, it's 68%. Okay, it's 68%. And so for, well, let's go back down here. So for this problem, this one, it would be 68%. And that comes from that empirical rule over there. So you've just got to draw it out, and you've got to see, okay, one standard deviation about the mean. And so I go up there and look, and that one standard deviation about the mean, 68%. All right, so that's question 1, or A, I guess you could say. So now let's look at B. Between 70 and 74. All right, so there's 70, 74. Let me see if I can, I don't know how this is going to work, but let's copy that. Let's paste it, see how it fits here. All right, so that way we don't have to keep going back and forth. All right, so we're looking for 70 to 74. And what we're finding is this area right here. So this right here, we can see is one standard deviation, right? That's one standard deviation because that's 4 units and a standard deviation is 4 units. So if you look at this, what we're looking at here is we've got just this, right? Well, remember, this curve is symmetrical about the mean. Okay, it's symmetrical about the mean. So if from here to here is 68%, then from here to here, this part is going to be exactly half of that. Okay, so this one would be 34%. Okay, see, it's real it's real helpful to know this thing, this right here, because and I would say, you know, when you're taking a test or something, just sketch this out real quick. You know, put the -1, you know, just -3 to 3, and then, you know, the first one 68, 95, and 99.7. Just label it out so you'll have it there, and it makes these problems a lot easier to work. And so, and you can see it's really not memorizing anything of how to work something. It's just basically sketching it out and then going back and looking at this thing and just reasoning it out. Okay, so this is 70, and so we want to know, it's asking us above 78 inches, so they're wanting this part. You see that? So there's a couple of ways that we can do this, and I'm going to show you both of them because I want you to get I want you to make sense of how this thing works. So if you see both ways, hopefully it'll help you understand this curve better. And believe me, we're going to use this curve again in the next section too. All right. So first thing we've got to do, we need to determine how many standard deviations are we away from the mean. Well, this is 78, so, well, this is 74. That's one standard deviation, right? That's 4. And then if I go another 4, so I'm 2 standard deviations above the mean. And so if we look at this, we're actually looking for what? This area right here. I hope that makes sense. Okay. All right. So basically the area that we're looking for is this area right here, and that's all we need. Okay. That's it. So, well, what can we do here? Okay, how are we going to solve this one? Well, do you see? Let me see. Let's use. I guess we'll stay with the red color. So, do you see from here all the way to here? Okay, that is 95%. All right, that's 95%. So I know that the percentage, it's going to be the 95%. Okay, that's this part. That's 95%. Now, remember, we're trying to get to this or this. Well, I know I say that. I'll explain that in just a second. But we're trying to get to this. Well, do you see how we know, we know this part right here. Here. That's 95%. So, once again, I just need this part. That's all I need is this part right here. Well, that means that 100% minus 95%, which that is equal to 5%. That's what's left over. Because if you remember earlier, I told you the area under this entire curve is 1. Okay? So the 5% is left over. And that 5% is this is the area under this piece and this piece combined. Okay, that's this area and this area is 5%. Well, this thing is symmetrical. Okay, so this area and this area are the same. So if it's 5% left, okay, then that percentage is going to be 5% over 2, which is what? 2.5%. And that would be this area. And I know I said something about this area. Well, that's that area too. Okay. Sometimes it's easier to find this area over here than it is to the one that's going above the number. And that will make more sense later on in the next lesson. But anyway, that's what it is. I mean, you've got to draw this thing out and reason it out, figure it out, and it will get easier and easier as you work the problems. But for this problem, that's going to be 2.5% of the men are above 78 inches tall. Okay, so here we go, computing z-scores. Now, before we get on to this, we've been finding areas under these curves that are 1 standard deviation about the mean, 2 standard deviations, and 3 standard deviations. Okay, nice numbers, you know. And so you may be thinking, well, what if it's not 1, 2, or 3 standard deviations away from the mean? So in other words, what if, say, on this problem, they wanted to know for, say, 75. Okay, so for 75, greater than or between, or what if they said between 61 and 75? They wanted to know that area. Okay, well, adding 4 and subtracting 4 from 70 is not going to get us to 61 and 75. That's not 1, 2, or 3 standard deviations about the mean. That's some odd number. Well, that's what we're going to talk about some more in this section, and then we'll actually apply them to problems in the next lesson. But that's what this is, okay? Computing z-scores. Okay, so what this does is it shows us how to take a data item that we have, convert it to a z-score, and then we can find areas under the normal distribution like we were doing there. It's just what we have to do is see we convert it to a z-score because we're going to go look that up in a table. And like I said, looking all that up in the table and everything, that's in the next lesson. All right, so let's look at this. It says a z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. All right, so that's what we've been doing. Okay, remember we were going 1, 2, or 3 standard deviations above or below the mean. All right, well, what this is we may get 1.2 as an answer, or we may get negative 0.67 as an answer, and that's how many standard deviations that is above or below the mean. But this is telling us how to get it. So our z-score is whatever our data item is minus the mean divided by the standard deviation. So data items above the mean, they will have positive z-scores. Okay, so that makes sense. See, this data item, this value would be to the right of the mean, so it's larger. So a larger number minus a smaller number is going to be positive. And then data items below the mean will have negative z-scores. Well, if the data item's to the left, that means this number is smaller than the mean. So we got a smaller number minus a larger number is going to give us negative. And then the z-score for the mean, well, if this is the mean, then the mean minus the mean, that would be 0. And that's all that's telling you. All right, so let's see what we've got here. It says the mean weight of newborn infants is 7 pounds, and the standard deviation is 0.8 pounds. The weights of newborn infants is normally distributed. Find the z-score for a weight of... All right, so all they're wanting us to do here is just convert this to a z-score. That's all, okay? Now, and you might be thinking, well, I'm just converting it to a z-score. What is that doing? Well, you're finding how many standard deviations that is away from the mean, but this is going to be part of the process for the next lesson of solving these word problems and stuff that we get, these normal distribution word problems. All right, so let's write it down. We've got the mean is 7 and the standard deviation is 0.8. So, I mean, and the notation now, I mean, as far as the notation of how these books do this, I mean, some books will probably just put z equals, and then we've got the data item, which in this case is 9, minus the mean, which is 7, over the standard deviation, which is 0.8. And then that's going to be 2 over 0.8, which is 2.5. And that is your z-score. Now, the book I'm using, the way it does this is it puts that little subscript 9. I guess it's just putting that data value there. Okay, the data item is to let you know that Z9. I mean, if you want to put it, you can. If not, that's fine. Just do whatever your teacher tells you to on how to label that thing, or whatever your book does. So I guess what I'll do is I'll put this because that's what the book does. All right. So now we want to find what Z7. See, this is our data item. So remember, it's the data item minus the mean over the standard deviation. So this is going to equal the data item minus the mean, which is 7, over the standard deviation. And we can actually see that would be 0, right? 7 minus 7 is 0. And then let me guess, this one's going to give us a negative one probably. So Z6, that's going to be the data item, which is 6, minus the mean, which is 7, over the standard deviation, which is 0.8. And so this is going to be negative 1 over 0.8, which is negative which is negative 1.25. All right. So I hope that makes sense. And as far as these numbers go, let's see, 1 divided by 0.8. Yeah, 1.2. Now on these numbers, it came out to where, this was 1 decimal place, this was 2 decimal places. Now, the one thing I want to say about the z-scores, whenever you're converting a data item to a z-score and you punch it in your calculator, and let's say you get this whole big list of decimals, okay? You get a decimal with 8, 9 numbers behind it. Round it to 2, okay? Round your z-scores to 2. Now, I'm saying that for, if you're in my class. But if you're working these problems and you're looking the z-score up on a table, I know I keep mentioning table. It'll make complete sense on the next lesson when we start looking these values up. But the table only does 2 decimal places. Okay, so that's why you just round it to 2 decimal places. Now, if you want to be more accurate, yes, you can just leave all the decimal places, and then you can actually do these z-scores in Excel. You can look them up in Excel. So, if you needed to get more accurate. All right, so let's look at this next example. It says a student scored 70 on an arithmetic test and 66 on a vocabulary test. The scores for both tests are normally distributed. The arithmetic test has a mean of 60 and a standard deviation of 20. The vocabulary test has a mean of 60 and standard deviation of 2. On which test did the student have the better score? All right, so, obviously the first thing you're going to do is, he made a 70 on one of the tests, so of course that's a higher grade, but based on compared to the class and stuff like that, which one did he do better on? I mean, that's one thing. If you're in a class and you're taking a test, and let's say everybody in the class made in the 90s, okay, then that test probably wasn't that easy, right? I mean, it was probably too easy. But we're based on the spread of the data. That's what we're interested in. So let's look at this. Let's write down arithmetic test, and then let's look at the vocabulary test. All right. So for the arithmetic test, the mean was 60. That's what they give us here. And the standard deviation is 20. And then for the vocabulary test, the mean is 60, and the standard deviation is 2. And now, on which test did the student have the better score? All right, so let's see. On this one, he made a 70, and on this, on the arithmetic test, and 66 on the vocabulary test. All right, so we got all the information we need. So let's look at the z-score for the arithmetic test. So the z-score is going to be the data item, right, minus the mean over the standard deviation. And so that equals 0.5. And then let's find the z-score for this one, the data item minus the mean over the standard deviation, where that's going to be 6 over 2, which is 3. All right. So how did they do? Okay. So the arithmetic score was a 70, and that is half a standard deviation above the mean. See? So the mean is 60, and he made a 70, but this is a half a standard deviation. Okay? All right. So this one, what about this one? Well, the mean is 60, and he scored 66. All right. But this one is what? 3 standard deviations above the mean. And then see, this one's only a half of standard deviation above the mean. So we can see that the student did much better on the vocabulary test, but he's 3 standard deviations above the mean versus half a standard deviation above the mean. Okay? So that's how we can look at things with this, standard deviations and z-scores and all that good stuff. So what about IQs on the Stanford-Binet intelligence test are normally distributed with a mean of 100 and a standard deviation of 16. What is the IQ corresponding to a z-score of negative 1.5? All right, so basically what they're wanting to know here, so let's look at that. So we've got, let's draw the curve. And so the mean is 100. Okay, so there's your mean, there's your standard deviation. And they want to know what is the IQ corresponding to a z-score of negative 1.5. Okay, so this is negative 1.5 standard deviations below the mean. Okay, negative 1.5 standard deviations below the mean. Now there actually is a couple of ways that we could go about looking at this, but what I want you to understand is we're looking for this value right here, right? And it is 1.5 standard deviations below the mean. Okay. So what I want to know, okay, what I want to know is when I take the data item minus the mean divided by the standard deviation equals z, right? So I've got the data item, well, let's do it like this so I have enough room. The data item, which that we don't know. That's what we're looking for right here. But the data item minus the mean, right, over the standard deviation is equal to negative 1.5. And now we solve. So we're going to multiply 16 to both sides. So that's going to be the data item minus the 100, 16 times that. So that's going to be, let's just do this, let's do 16 times negative 1.5. And then I'm going to add 100 to both sides. So that's going to be the data item equals 100 minus 1.5 times 16, right? Because the negative times the positive is just a negative. And so that is going to give me 76, which the data item represents the IQ. Okay. All right, so I hope that helped. Well, the other way that we could look at it, and for this one, this one's kind of easy to look at like this. Some of them may not be as easy, but remember, we're trying to get to this data value, and it was what, 1.5 standard deviations below the mean, right? So if I go 1 standard deviation, that means this distance from here to here, that would be 16, right? That's 1 standard deviation. And then I have to go what? Half a standard deviation, which, what's half of that? And then I would be going 8 more, right? So basically that's 24. So you can see 100 minus 24, that gives you the 76. That's all you're doing, okay? But sometimes you may get some that are, that's 1.2 or 0.67. So you're not going to be able to really look at it you can, but it'll be more difficult to look at it like that. So that's why I'm showing you the best thing is, you're looking for the data item. That's what you're looking for. So you just plug it back into that formula. Your data item minus your mean over your standard deviation equals the z-score, and then just solve for your data item. All right, so how about this? And Mensa is a group of people with high IQs. Those members have z-scores of 2.05 or greater of the Stanford-Binet intelligence test. What is the IQ corresponding to a z-score of 2.05? All right, so let's look at this. I know the mean is 0, and we're coming out here. It's 2.05, and remember, we know it's over here to the right because the z-score is positive. See, remember, if we have a positive z-score, it's above the mean. If we have a negative z-score, it's below the mean. All right, and from here to here, this is 2.05 standard deviations above the mean. Now notice how I put the standard deviation here. I'm not calling this just 2.05 because that distance is not 2.05. It's 2.05 standard deviations. Okay? So, just like in the last one, I've got my data item. And I tell you what, for this problem, yeah, it's data item, but let's just go ahead and call it the IQ, our IQ score. That's what it is, right? Minus what? Minus the mean, which is 100, over the standard deviation, which I forgot that's 16. And that equals 2.05. Okay? And so now we're just going to solve. So I've got the IQ minus 100. That's 16 times that, which is 16 times 2.05. And then I'm going to add the 100 to both sides. So IQ is 100 plus 16 times 2.05. And so when we punch that into our calculator, we get a 132.8 would be the IQ score. All right. So you can see on this one, you would have to go 2.05 standard deviations. So it's you would go 16, 16, and then just 0.05 of that 16. So you can see how it's probably just easier just to put everything into that and solve. And that's really all you're doing. All right, so percentiles, we're not gonna get into a lot of it. Basically just mentioning it in here. So percentiles, it says if n% of the items in a distribution are less than a particular data item, we say that the data item is in the nth percentile of the distribution. Okay, and there's really no problems we're working or anything like that, but just kind of explanation. Just this is what it means. It says the cutoff IQ score for Mensa membership is 132.8. Is in the 98th percentile. So the cutoff IQ score for Mensa membership, 132.8, is in the 98th percentile. What does this mean? All right. So it's in the 98th percentile. So what it means is that 98% of IQ scores fall. Okay. So here's your, and I'm guessing they're referring, all these items back to the previous problem, the one that we just did. Okay. So what that means is that 98% of IQ scores fall below this value here because it's telling us it's in the 98th percentile. So 98% of scores fall below that score. So you can see if you make, up there at that score or above, you're doing pretty good. Now, a score in the 98th percentile, that I want you to be careful here because that does not mean that 98% of the answers are correct. And that does not mean that your score was 98%. Okay, that's not what that means. That 98%, it's not you got 98% of the answers correct on the test or you made a 98% on the test. It means your grade that you made, 98% of the other grades are below that. That's all it means. All right. And then there are 3 commonly encountered percentiles. I'm going to put my E there, or the quartiles. So the first, second, and third quartile. So the first quartile, well, what does that mean? So the first quartile means 25% of the data fall below the first quartile. So, and this right here would be your, let's do it in a different color. This would be your first quartile right here. This would be your second quartile, and this would be your third quartile. See, the second quartile, 50% fall below. There's your 50%. The third quartile, 75% fall below. Okay, and another way that you might see it written in some statistics books is Q1, Q2, Q3, first, second, and third quartile. And that's all that means, See, there's your 75% below. It's just breaking it up into fourths. Now let's talk about margin of error. And we're almost finished, so just hang in there. It says if a statistic is obtained from a random sample of size n, there is a 95% probability that it lies within 1 over the square root of n times 100% of the true population percentage, where plus or minus 1 over the square root of n times 100% is called the margin of error. All right, so let's just let's look at this as an example. Let's just go straight to the example. It says in a random sample of 1,000 U.S. adults, 46% of those questioned said they dread public speaking. Verify the margin of error that was given for this survey. All right, so let's find the margin of error. So you can see that our margin of error is plus or minus, right? It's right here, okay? 1 over the square root of n times the 100%. Okay? So the margin of error is plus or minus, write that a little better, plus or minus 1 over the square root of that 1,000. Yeah, n is 1,000 in this case, times the 100%. So that is going to be plus or minus. So when we put that into our calculator, we actually get 3.2%. This is our margin of error. Okay, that's our margin of error. Now, what they're asking us here in part B is write a statement about the percentage of adults in the U.S. population who dread public speaking. All right, so we found our margin of error to be 3.2%. And it says 46%, and it says in a random sample of 1,000 U.S. adults, 46% of those questioned said they dread public speaking. All right, so we found our margin of error. So that means if we take the 46% minus the margin of error, and we take the 46% plus the margin of error, so if we subtract it, that is 42.8%, and then this one is 49.2%. Okay. So what does this mean? Okay, so this is going to kind of explain to you what this is. Okay. So we found our margin of error to be 3.2%, and then we subtract and add. So what this means is we can say with 95%, right? See, 95% probability. So with 95% confident, or well, let me say, we can, let's write it like this. We can be 95% confident, right, that between 42.8% and 49.2% of all U.S. adults dread public speaking. All right, so that's what it's doing. We're finding the margin of error. So we can be 95% sure, 95% confident that 42.8 to 49.2% dread public speaking. Okay, it's not 100% confident, but it's 95%. Okay, and we in a contemporary math class, you don't really do this, but This gets more involved with confidence intervals and stuff like that. I mean, if you're interested in it, go take you a statistics class and you'll learn more about that. But yeah, but that's what it means. Okay, that's what it means. And then I just want to mention this real quick. Distributions. You've got, we've been talking about a normal distribution, where you've got that bell-shaped curve and it's perfect. Well, you may have some that are off to the side. See how the highest part is more over this way, and then here it's more over this way. It's kind of like you just drug it over here and then drug this one over here. Well, these are called something. This is called skewed right. Okay, and this one is called skewed left. I know it looks like you would call them the opposite, right? But we're calling it skewed right. That's where the tail is. We'll call this one skewed left. That's where the tail is. Okay, and that's really all of this section. Like I said, this right here is kind of like a quick, brief overview of things. Okay, and we'll really get in there working some problems next time. So, all right. So I hope that I hope everything you understood it. Check out my other videos. Give me a like, share, and subscribe. And thanks for watching.